Okay, so resonance structures. So let's see. You guys remember when we talked about isomers? Glucose, galactose, fructose. That's right. I'll remind you. Let's see. Can you guys see my screen?
Yes.
Yes, I can see it.
Okay. So glucose is a 6-carbon ring structure. Okay. Where each of these points represents where a carbon would be. And let's see. Except if there's an O there. Oops. One, two, three. Four. 1, 2, 3, 4, 5, 6. And fructose is a 5-carbon, a 5-ring structure sugar. Okay. Now the chemical formulas are exactly the same. C6H12O6. C6H12O6. Can you guys hear me? Because it keeps showing me that my audio is screwed up.
Yeah, okay.
I can hear you just fine.
Good. Fructose is primarily found in fruit. Glucose is found in beets and pure cane sugar from Hawaii. No, actually, that's sucrose. But beets and there's something else that is high in glucose. Okay, so can you see the structural difference between the two? I mean, it's a crude drawing, I know.
Yes.
Okay, so this is an example of an isomer. It has the exact same chemical formula, right? But it has different structures. Now, they also behave differently, right? How they're going to interact with things. Also, there's a slight difference in taste. even though they're both sugars. Okay, so a resonance structure, because electrons are constantly moving, we have the possibility of having Lewis dot structures that will be equivalent to each other, right? And then the only thing that's changing is the position of electrons. So let me give you an example of a resonance. Okay, so here we have SO3. Okay, if you look, we have the double bond is located. We'll call this the 1 oxygen. This will be the 2 oxygen, and this will be the 3 oxygen. The double bond is located where? And this in A.
Third oxygen.
Okay, and then here,
Second.
and then in C.
Oh, it's ABC. Oh.
Yeah, I'm just saying ABC, just to make
Oh.
it easy for us. Where is the double bond located?
First one.
On the first one. So this is an example of resonance structure. All of these forms actually will exist, right? Because the electrons are constantly moving. So, and you also have several molecules. One will be in that third carbon. One will be in the second carbon, the third oxygen. One will be in the second oxygen, and one will be in that first oxygen, okay? And so they all exist. So that's called a resonance structure, okay?
There
And
are
really
double bonds in all the images, Professor?
What was that?
Isn't there a double bond in every one of those images?
Yeah, but look where the double bond is located,
Oh, okay.
okay? And the fact that that double bond is located in different locations is what makes it resonance. So this guy, and that guy are going to be slightly different. Here it doesn't seem to make too much of a difference because you have three oxygens. But if we had that fourth oxygen, where it was going to be located at would actually make a huge difference, right? Okay. So, and that's just an example of a resonance structure. Okay, so you guys been working really hard to understand Lewis dot structures, right? You're feeling confident in it?
Somewhat.
Somewhat?
Yeah, somewhat.
Sorry, I haven't had a chance to eat anything, so I'm starving. Except for this morning. Well, keep working on it. You're going to get it, and you're going to need it. Because the next part that we're going to be talking about is geometry. So electron pair geometry is, we're talking about the geometry of the molecule. And electron pair geometry takes into consideration the electron pairs, as well as the atoms that are forming bonds between the atoms. As well as the bonds that are formed between the atoms, okay? So VSEPR, which stands for valence shell electron pair repulsion theory, right? So the way it works is the electron pairs are going to try to repel each other as far as possible. So they're not going to want to be right next to each other. So when we draw our Lewis dot structure, let's say we're talking about C, although there's no electron pairs here, right? Well, these atoms, the hydrogens, they're going to try to be as far away from each other as possible, right? And again, this is a three-dimensional structure, although it looks like a cross. Really what it looks like is you have any of you guys ever played, what is it? the balls and the jacks that with the ball and the little
In high school.
Yeah.
in high school?
Mm-hmm.
Okay, so you know the little jack, it has 4 sides to it.
Yeah.
Okay, so those 4 sides, the fact that it has 4 attachments to it, that would be called a tetrahedral, right? And so there's a 3D structure, and although mine isn't the best one shown here, this is what it's going to kind of look like, right? You're going to have one that's going to be going up. You're going to have 3 that are kind of in the same planes. That forms kind of like a pyramid.
Kind of
Right. What was that? Kind of like a pyramid, you said?
like a little like a chicken foot.
Yes, like a chicken foot, exactly, like a chicken foot. So the angle is going to be 100 degrees. I'm sorry, not 120 degrees. It's going to be 109. I'm on.
And are these going to be for like, is it universal like for all of them, or is it just an example?
This is an example, but it's for this one particularly. So if there are 4 attachments, it's going to be roughly 109. There are going to be some modification. So let's say water, Lewis dot structure for water is okay. So this molecule, you have 2. Show this like this. You have 2 electron pairs, right? So these electron pairs, they're not going to want to be right next to each other. They're going to try to push each other as far away apart as possible. Because they're pushing each other, these 2 electron pairs, and these lines just kind of represent like little antennas for the electron pair, so you know that they're electron pairs. And I'll show you another figure here in a minute that'll kind of clarify that. These guys are not going to want to be right next to each other. They're electrons. They're going to want to be away from each other. And because of that, that's also going to push the rest of the structure. So that's going to cause this guy to be pushed down the way it is. So it has a bent structure. Do you see the bent structure?
Yeah.
Okay. So the way that we determine our geometry is by the number of attachments that we have. So when we're talking about electron pair geometry, we're taking into consideration that we have, in this case, each electron pair counts like an attachment. So this would be 1 attachment. That would be 1 attachment. This would be an attachment. This would be an attachment. So how many total attachments are there?
4.
4. So when there's 4 attachments, we refer to this guy as tetrahedral in terms of the shape. So it's going to form a shape similar to this. Now the electron pairs, they're not visible in terms of the molecular geometry. They're kind of invisible. But because they do exist and they cause that bend for those atoms, the structure here, the molecular geometry, is going to be bent. Because the electron pairs are not going to be visible to us. So all you see are the attached atoms. And so you get a bent structure. Where the electron pair geometry, you have 1, 2, 3, 4 attachments. It recognizes that there's 4 attachments. So then the electron pair geometry would be tetrahedral. Now, don't worry about that you don't get it yet. After we finish, I'm sure it'll start clicking here. Tetra meaning 4. Hedral meaning sides. Okay?
Pair geometry.
Okay, so up here we have 4 attachments. The molecular geometry is going to be 4 things attached.
Tetra.
That's right. So it's going to be tetrahedral. And the electron pair geometry would be exactly the same because there's no electron pair. You just include the attachments. So it would also be tetrahedral. Okay, so electron pair geometry, you include the atoms as well as the electron pairs. Okay,
What do you mean by that?
so here we have 2 electron pairs on the oxygen, right?
Yeah.
So when we count for the electron pair geometry, we want to count the electron pairs as well as the hydrogens. So that's 1, 2, 3, 4 attachments. So that guy, his electron pair geometry would be tetrahedral because there's 4 attachments.
Oh, okay. All right.
Do you
And it's
get that now?
molecular, would just be bends.
Yep, it's molecular geometry. So that's just like if you're seeing it without the electron pairs. So if it was just drawn like this, without your, which is, sometimes early on when I was drawing it, I drew it without the electron pair. You can see that it's bent. And I draw it bent because I know, I call it Mickey Mouse ears, right? I draw it bent because I know that it has electron pairs that causes it to bend. Okay. Okay, are we good so far?
Yeah.
Yeah.
Good, clear. So, yeah, I'm just going to kind of give you all of the terms, and I'm just going to be throwing them at you. Okay, you got to catch fast. So, if our electron pairs are directly opposites of each other, and it forms a 180-degree angle, we know that that's linear. If we have 3 attachments, 3 electron pairs that are around each other, this guy is going to be called trigonal planar. Meaning that they're all in the same plane and you have 3 attachments. This guy has 4 attachments. What is that called?
Tetrahedron?
Tetrahedral. Okay. Okay, so here, this is just balloons basically showing you the same thing. So if you have two balloons tied together, they're going to form a linear structure. So if you have two atoms that are interacting together with a single bond, it's going to be a linear structure. Okay. Oops. If we have three things attached, right, and they're going to form that 120 angle, that's going to be trigonal planar. This one, you have four attachments. That's going to be tetrahedral. Can you guys see it?
Yes.
Okay, so this is basically showing you our geometry. Now, one is just looking at the electron pair geometry, which is shown here. And this tells you, okay, so here, if you have two things that are attached to each other, it's going to be linear. Here's an example of it. And then here's an example of a linear molecule. So if your center atom has two things on the opposite sides and there's no other electron pairs on here pushing it any direction, that guy is going to be linear. Okay, and here's an example, BeFe2. Okay, so this guy is showing you basically trigonal planar for your electron pair geometry. So if I have three things attached to that center atom, and again, there are no electron pairs, this guy is going to be trigonal planar. An example is BF3, boron fluoride. Here, this is an example of, again, trigonal planar, but in this case, we have a single electron pair. So you see that electron pair up there? Now there's two attachments. Double bonds counts as only a single attachment because it's attached to one atom, right? So that's 1, 2, 3. So the electron pair geometry is trigonal planar, but the molecular geometry, because we don't see the electron pairs when we draw when we have the molecule, that's what we're showing here, it's just going to be represented as bent or angular. Okay, an example of that is SO2. So here's an example of 4 attachments. Tetrahedral. And then this is just another example. Methane is the example that is commonly used. Here again, the electron pair is tetrahedral, but we have a single electron pair up top. So in this case, this guy is going to be called trigonal pyramidal because that electron pair up top is pushing those attachments, those other atoms down. An example of this is ammonia. And then my last example. So again, you have 4 attachments, including all the electron pairs. Here we have 2 electron pairs. So again, this guy is going to be bent. It's going to be pushing those other 2 atoms down in terms of the molecular geometry. Okay. But the electron pair geometry is tetrahedral. So Matt, what do you think? Do you think you got it?
I think so. It certainly makes sense.
Erica? Cool.
Professor, could you go over number 3 again? I got the first part, but I didn't catch the last part where you were telling us that the double bond only counts as a single attachment. And then the other attachment is what makes it a angular or bent, correct?
That's right.
Okay.
So since we have a double bond, it's the bond between the A and the B. That's only one, even though it's a double bond, A is attaching to B. So it's considered a single attachment when
Okay.
we're talking about molecular geometry. Okay. So that's one attachment, and then it's attached to this other A. That's your two attachments. Now, the electron pair causes it to be shifted, right? But visually, we don't see that electron pair. When we look at the structure, we just see those two atoms, okay? And so our molecular geometry is going to be bent because of that. Even though that technically there's, if we look at the electron pair geometry, this guy is going to be trigonal planar because there's three things attached to that center atom. So here's B, you have 1, 2, 3 attachments when we look at the electron pair geometry. But when we look at the molecular geometry, it's as if there's only two things attached and it's just in a bent structure.
Okay.
Okay?
Eric,
Yes.
so it can also apply to single bond on both and not.
Yeah. Yeah. Like up here, we have a single bond, 3 single bonds, right?
Mhm.
So this guy, that's 3 attachments. So the electron pair geometry is trigonal planar, and the molecular geometry is also trigonal planar.
I mean on the molecular geometry on the third one that is angular or bent.
Yeah.
On one side we have single bond, on the other side we have no, not that one.
Not this one?
Line 3. Yeah.
Okay. So you're saying if I had something that was like this.
Yeah.
Yes. So it would still be bent, but it wouldn't be as bent. You know, so the angle would change because in this case, these guys are still going to be pushing down a little bit.
Yeah.
But it's not going to be much. And so really, this guy's going to be really close to 120 in terms of the difference between the gap, right?
Okay.
Okay. Okay, so this here is just basically showing you that for electron pair geometry, all of these guys are considered tetrahedral because it's the electron pair. 4 attachments, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Now for the molecular geometry, they're different, right? So this here is the molecular geometry. So this guy is tetrahedral because you have 4 true attachments, atoms that are attached. This guy has 3 atoms that are attached, and you have that lone pair that's pushing things down. So that's going to be trigonal pyramidal. And then we have the case of water, which has 2 lone pairs pushing things down. And then you have your 2 attachments to hydrogens, right? So that one's going to be bent. Okay? Okay, so often we haven't talked about this, but because we're drawing 3-dimensional structures, we need a way to draw 3-dimensional structures because this ain't cutting it, right? Where I have C, H, 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 and H, right? So that isn't going to be good enough because we can't tell if it looks like a cross, right? Your first instinct saying, oh, I have one up here, I have one here, and I have one there, but it's not like that, right? So we are going to use what we call the wedge and dash diagram, okay? Okay. So here's an example of the wedge and dash diagram. As you can see, that the nitrogen is there in the center, right? That's our center atom. We have, you guys have the bars on your cell phone to let you know how much of a signal you have?
Yep.
Okay, so you have the bars on your cell phone to let you know how much signal you have right here, right? So that guy is going towards your back. The guy, the bold line, that one is coming out towards you, right? So you have the one that's going forward, the one that's going back, and then this guy is going to be the one that's in the same plane, okay? So it's like next to it. They got one forward, one back, and one like this on the side, okay? So can you guys visualize that?
Yeah, and is that something we have to like take down? Is that how we're gonna be doing our like work when we turn things in?
You need to be familiar with it. You also need to be able to recognize it, and you should be able to draw it, right? If it's asked for, or recognize it at least on a multiple guess, you know? So, draw methane. On your paper, draw methane. Everybody has a figure? Yeah, no, maybe.
Wait, do we have ready? Because I know mine.
What was that? You have yours ready?
No, not yet.
Okay.
The one with the lines, right? The multiple lines, what is that one, forward or?
That's backwards. This guy, your
So that
Wi-Fi
one's
signal,
back.
that's backwards. The one with the thick line, that one's coming at you, right? Or forward. Now, I'm going to use an exclaimer here. I am not an art major, so you know. Okay,
And then
So what
the thin line one is one.
that one is like right next to you in the same plane. Okay, so like here, you're the molecule, right? And your hands are going to represent. So yeah, the one that's in front, that's going to be the bold line one. If you put your hand in back of you, that's going to be the one that's the Wi-Fi signal. And then the one next to you, this way, that one is going to be, or that's in the same plane as you, that one is going to be the line, okay?
So essentially, we're gonna have two Wi-Fi signals then, because we're gonna need two in the back and then the one in the front and then the one off to the side.
Yep. Because also remember, you also have above you, right? So the way you would draw it is, you would have your one that's above you. You'd have your thick line. Okay, again, I am not an art major. You'd have your Wi-Fi. And you'd have your guy that's in the same way. Okay. So what is for the N here, this NCCl? So the Lewis dot structure would be, it would have these two electrons on top of here, right? So what shape would this be? What would be the molecular geometry?
Would it be the tetrahedral?
The molecular geometry, not the electron pair geometry.
That one would,
Trigonal pyramid?
Is it angular bend?
There we go, trigonal pyramidal. That's right. So this guy would be trigonal pyramidal. And this guy would be
That one would be the tetra, right?
that's right. This one would be the tetra. Okay, so now Matt, tell me the electron pair geometry of this guy. And we'll use for abbreviation, electron
No.
pair. So we'll call it EG, electron pair geometry. It's gonna be
Then it'll
what?
be tetrahedral.
Tetrahedral. And then this guy, what would be the electron pair geometry of this guy?
Tetrahedral too.
That's right. Okay, piece of cake.
did you give us like an example of the tetra or whatever that middle one is, the pyramids, whatever it is in the middle?
Trigonal
And see-
pyramidal.
Yeah, how did I miss that? I mean, I didn't even see that you told us what that was or what it looked like. Is that on the slide or something?
It's on the slide. You want me to point it out to you again?
Oh, I guess I didn't get it. No, I can just go look for it myself.
Okay. So we have, this is trigonal planar. This down here is trigonal pyramidal. See? It's just on its side. If you flip it, and you got to think about things in 3D, we can move them around, right? Okay, questions, concerns, Cash?
I had a question.
Okay.
How do you determine if that element's moving towards you or it's moving away or it's in the same place? Is it the bonds it makes?
Yeah, it's the number of bonds it makes. So if it has 4 bonds, you're always going to have one going up top. You're going to have one that's going out forward and one in the back and one in the same plane. But those guys are going to be kind of pushed down a little bit. Kind of like, let me show you. Like this. Okay. One
Okay.
front, one back, one in the same plane. And
Okay.
then you got your thing up top.
All right. Got it. Thank you.
Think about a jack, right? Go out and buy some jacks. You know, I think you could get them at the dollar store for like $1.
I have a question too.
Okay.
For the CH4, when you had the Wi-Fi's on the left side, is
Yeah.
it the same thing if you switch it to the right side?
Yeah, technically it would be, because it's just, hey, I'm a lefty and you're a righty, so
Yeah.
you may draw it a little bit different. Long as you have one that's coming forward and one that's coming back.
Oh, okay.
So right now it's not going to make a difference, right?
Okay.
Because it's essentially the same in this case. But we will start making structures where it's going to make a difference. Okay.
Dr. Henry.
Yep.
This the methane, the first one.
Yep.
And the one on top, are they the same?
What do you mean by the one on top? I'm confused.
Sorry, there's one like I see it has net around it. The one beside the let me, sorry. You know, there are two structures here in a box. The two structures in each box, are they the same?
This structure here? This
Yes,
structure here?
no. In the same place, in the same box.
Oh, this one right here?
Yes,
Yeah.
yes.
So yeah, this is just showing you it has 4 sides. 1, 2, 3, 4. So that's where you get the tetrahedral from. This guy technically will have, so here it shows it also, you have 4 sides, right? So that's talking about your electron pair geometry, right?
Okay.
But when you look at the molecule, you only see those 3 sides,
Oh, okay.
okay?
All right.
Okay,
Thank you.
you're welcome. Okay, let's see. Okay, so what happens when we have multiple bonds? Okay, so how is that going to change our wedge diagram? How is that going to change our geometry, right? So the way that you handle that is when you have, let's say, I shouldn't say multiple bonds, but like, let's say we have C2H4, where we have 2 center atoms. Okay, so what is the Lewis dot structure going to look like for this guy? Now, don't all you guys,
Carbon is going to be in the middle.
carbon's going to be in the middle.
Then the fluorine is going to be on top.
You mean the hydrogen? There's
I
no
mean,
fluorine.
sorry.
Yeah.
Oh, the hydrogen, I'm sorry. The
Okay,
hydrogen will be there.
okay,
Then down there.
okay,
Then double bond,
okay,
another C. Then hydrogen. Then hydrogen. No.
okay. So you look at each
1,
center
2, 3,
atom.
4,
What is the
5, 6,
structure
7, 8, 9, 10.
that's going to be given by each center atom? So look at this carbon. There are how many attachments?
Okay. 1, 2.
Right.
There's 3 attachments, right?
Yeah, 3
So then
attachments.
what is going to be the shape?
It's gonna be is it tetra?
Oh, right.
No, triangular pyramid.
Triad.
Trigonal,
Trigonal what?
pyramidal.
Pyramidal? Is there something that's pushing it down? You have lone pairs pushing things down?
No.
No.
I think it's
No?
gonna be tetra.
Trigonal planar.
Trigonal planar, meaning that they're all in the same plane.
Okay.
So this guy is going to be trigonal planar, and this guy is going to be trigonal planar. So basically, it's like a flat sheet of paper. That's what we mean by in the same plane. It's all flat. You don't really have like a 3D component to it. Everything is in the same plane. Okay? So it's just going to look like that. There's not going to be any wedges or dashes because the wedges and dashes gives us our 3-dimensional aspects. Are we good? You got it?
You said we do those individually?
Yeah,
On
so
the
you do
center atom?
each center atom individually. Okay, what if I have this guy? Let's see. That guy. So what is the Lewis dot structure going to look like?
Your carbons are all going to be in the middle. And
Okay, so
they're
my
gonna
carbons are going to be in the middle.
each other.
Oops. So I have my 3 carbons in the middle. Okay. And then
the first carbon's gonna have 3 hydrogens.
okay.
The second, it'll connect bond to the other carbon, and then the second one will have 2, one on top and one at the bottom.
Okay.
And then the last one will have 3 as well, just like the first one.
Okay. So this is our Lewis dot structure. What will be the wedge? The dash wedge or wedge and dash diagram.
It's gonna be trigonal pyramid.
Is it going to be trigonal pyramid?
Wait, hold on. No, I lied. It's gonna be tetrahedral.
Tetrahedral. And the next one?
The next one would be
How many attachments?
that's the 3-pair one, so that's probably the trigonal one.
How many attachments does it have?
Do we count the first one?
It's attached here, yes.
Okay.
Tetrahedral.
So it's also tetrahedral. That's right. And then
Okay.
the last one is going to be tetrahedral. So you have 3 tetrahedrals. So you would draw it. That's going to be 1H. And then we have our dash. 8 dashes.
Be quiet.
You're going to have the one up top. Then you're going to have your other C. And then you're going to have the one on top. You're going to have one that's your dash. And then your sorry, this guy is going to be your other C. And then you're going to have the one on top. Okay. Questions? I know it's crazy, huh?
The last carbon has how many? 1, 2, 3, 4 hydrogen.
Oh, I got carried away. I was being greedy. So yeah, my bad. Good eye, good eye. Gotta keep me honest. Okay, questions, concerns, Cash.
Yeah, that drawing kind of confused me now.
So remember, it's just because you have 4 attachments. So you have the one that's going to be up top, you have to be the one that's going to be coming out front, the one behind, and then this is going to be the one right next to it. One up top, one out front, one behind. And then you have the next carbon, and it has one up top, one out front, one that's in the same plane. So
Okay,
since this
got it.
guy was sort of,
All right, thank you, I got it.
okay? Questions? No questions?